Alrighty. All right. First things first, you guys are gonna have to forgive me. This is the first time I've done like a live streaming type of flipped classroom thing. So I have no idea if this is gonna work out particularly well at all. But we're gonna give it the old college try, as they say. Okay, so first thing I gotta do is I gotta have to you guys gain access to my screen. So I should probably come up with a paint first. We're gonna be doing a lot of drawing. Cool. Alrighty. And I think I can share here. Let's find out. And I would like to share. The paint. Lovely. Okay. We'll go with that. Cool. Alrighty. So this is what we're going to do today. We're going to spend a little bit of time. Okay, sorry, I'm just orienting myself right now. Okay, maybe I'll edit this in post, but probably not because I'm not that technologically savvy. Okay, so what we're going to do today is we're going to talk a little bit about chemical nomenclature. The reason why I'm doing this chemical nomenclature one as a flipped classroom is that there's just a whole bunch of rules that unfortunately you just have to memorize in order to understand how to name different kinds of molecules. So what I'm going to do is I'm going to try breaking down the rules here. And then in class, what we're going to do is we're going to do a bunch of practice problems associated with it, and then probably do some other practice problems associated just with recall, just so we're good to go for the upcoming exam. Let's do first. Okay, I guess we could just jump right into it, I suppose. Okay, so where should I start with? Okay, maybe we can do this. All right, so the molecules generally fall in two broad categories. Let me pick a pen that is workable. Calligraphy brush feels right. Yeah. Into two broad categories, and these would be organic. Yikes. It's quite a choice for a pen. Let's go to 2. There's organic, and then there's inorganic. Okay. Now the organic side of things, I guess both of these have very, very different styles or conventions with respect to how they're named. The organic one, you're going to learn all about that whenever you take organic chemistry, which we all know you are. So I'm not going to talk about that one today. Instead, what we're going to do is we're going to focus primarily on inorganic molecules. Okay, so how do we go about naming inorganic molecules? So we're going to go ahead and erase the organics for now. Ooh, I have to make that bigger. Here we go. There we go. Now, inorganic molecules come in 3 broad flavors that we need to talk about. The first of which is ionic compounds. Oops. Ionic compounds. The second would be acids. And then the third would be molecular compounds. The ones that are the most important and require the most explanation are going to be the ionic compounds and then the acids. Okay, so we're going to focus primarily on those for today. There we go, 1 and 2x. Okay, so let's get started. Recall that within ionic compounds, there's 2 pieces to them. There is some kind of cation component, which is positively charged, and there's some kind of anion component, which is negatively charged. Okay. These different cations and anions that can come in, they can either be just individual monatomic cations or anions, or they can be polyatomic. So example, we have something for the cations, we can have something like sodium or magnesium or 2+, or ammonium. And on the anion side, we have something like chlorine, oxygen, or nitrate. Okay, so two broad bins of things. So we need to take both of those into account if we're ever going to start naming ionic compounds. Okay, so what I'm going to do is I'm going to take care of the cation side first, explain the ways that you named cations, and then the anion side. Okay, I'm going to erase this here. Actually, no, I'll leave that up right now. And then, okay, good. And then I'll send you I could just send you the whole thing at the end. So on the left here, we're going to talk a little bit about the cations. So when you're naming cations, it's actually really, really straightforward. So let's take the different examples that we talked about. So let's say sodium, let's say magnesium, let's say ammonium. Okay. And you know what, for the purposes of our argument, we'll go this to put this to the side. Okay, so the primary way that we name cations or reference cations whenever we're naming ionic compounds, it's really straightforward. You just describe the element or molecule involved. So if we have this guy right here, we would call this a sodium ion or a sodium cation. This would be a magnesium cation. Okay, this would be an ammonium cation, and so on and so forth. Okay, that's not too bad. Sodium cation, zinc cation, aluminum cation, whatever the case may be, right? We just name the element or the molecule, and then we're Gucci. Now, there are some types of cations, right, that can have differing amounts of positive charges. Okay, I think maybe we mentioned this in a previous lecture, but I'll reemphasize it here. Especially within the transition metals, you can have elements that can take either like a +1 or +2 or a +3 charge. So for example, iron can exist as iron 2, or it can exist as iron 3. And we represent which positive charge it has at any given time using these Roman numerals. Okay, so we would call this iron 2 or iron 3 or something like that. Okay, that's the only other really big delineator whenever we're talking about cations. Okay, so we'll reference the charge of the cation using a Roman numeral. But other than that, it's really straightforward. This is still an iron cation. It's still an iron ion, right? This is still a sodium cation. This is still a magnesium cation. You don't really have to change the name of it really at all. So that's not too bad. There are some old school conventions that are worth mentioning here, just if you see them. I'm not going to like be asking you to memorize these or anything like this. Like it won't show up on an exam, but it's something that will possibly show up like in lab or something like this. So I just want you guys to be aware of this. So for example, if we have a iron 2, again, that means that the charge on this is +2, in this case, +3. Old school conventions would also add a suffix to these. So the way this would work is if you had a smaller positive charge, you would add the suffix us, whatever, to that thing. And then for the higher of the positive charges, you add an ick. Okay. Us and ick are going to show up later on when we start talking about acids. So this is one other reason why I don't want you to stress too much about it, because it's just becomes needlessly confusing. But in general, the us meant that it was the less positive. And then the ick meant it was more positive. Okay, so for example, if I had copper 1 and then copper 2, then this would be cuprous cation, and this would be cupric cation. Oops, cupric, not cupic. Okay, similarly, this would be ferrous iron, and this would be ferric iron. Okay, so the "-us" suffix means less positive when we're talking about cations, and it means more positive if it's "-ic" when we're talking about cations. Okay. Now, let's see. There are a couple of cations that I want you to have memorized. So I'm going to scroll down here and then set up a new spot. More bigger. There we go. Okay. All right. So the cations that I want you to have memorized are as follows. Cations by Dr. K. All right. So in the +1 version, I want you to have the hydrogen memorized. I want you to have the sodium memorized. I want you to have the potassium memorized. I want you to have the silver memorized. Okay, so these are all +1s. For the +2s, I want you to have magnesium memorized. I want you to have calcium memorized. Zinc. And then there's a series of, yeah, let's do these ones too. So then copper. These are just the more common ones. Lead. And then iron, like we just described. That would be ferrous iron. Okay, so these are all +2. As far as +3 are concerned, there's only 2 that I want you to have locked in, and that is the aluminum. Excuse me. I almost did a Britain. And then ferric iron. Okay. All right. Also, I'll go ahead and add ammonium up here because that's kind of important too. That's the only polyatomic one that I want you to have down. Okay, so these guys for the +1, these guys for the +1, these guys for the +2, and these guys for the +3. Okay. But other than that, the naming conventions for cations aren't too awful. Things start to get a little wonky when we start dealing with anions. Okay, so let's mosey on over to the anions side of things over here. All right. And the reason why is that anions, there's a lot of different kinds of polyatomic anions. And specifically, they come in a couple different flavors. So there's monatomic. That's the one much like the cations that we see over on this side where it's just one atom. Right? But then they also have a bunch of polyatomic ions, and there's a large class called oxyanions. And what happens in an oxyanion is it's some combination of oxygen plus some other element. So this would be something like chlorine, nitrogen, carbon, whatever the case may be. So that's an oxyanion. There's a whole bunch of polyatomic oxyanions. So they have a sub-naming convention we're going to address in a second. But those are the 2 broad bins for anions. The monatomic anions are actually pretty straightforward. Let's consider a couple of them. So let's say I have something like H-1 somehow, or chlorine -1, or oxygen 2-, or nitrogen 3-. Okay, these are all different kinds of monatomic anions. The only thing you have to do for a simple monatomic anion is remove the suffix at the end and then replace that with an "-ide." Okay, so hydrogen goes from hydrogen to hydride. Chlorine goes from chlorine to chloride. Oxygen goes to oxide. nitrogen goes to nitride. Okay, in each of these instances, again, this is specifically for monatomic ones, right? All you got to do is cut off the end and replace it with "ide." So this is where we get our chlorides, fluorides, bromides, iodides, all these kinds of things. Okay, so that's not too bad. Where it starts to get mixed up, as I mentioned, is when we're dealing with oxyanions. Okay, now here's how it works. Let's consider a normal oxyanion, like nitrate or something mixed with nitrogen. Right. What will oftentimes happen is you'll have nitrogen blending with a certain amount of oxygens, right? And then you'll have nitrogen with a different amount of oxygens. Oh, excuse me. Let me erase that real quick. Sorry. Let me try re-explaining that portion. With oxyanions, sorry, let me try that again. With oxyanions, essentially how it works is you'll have the non-oxygen atom, in this case nitrogen, right? And it can blend with multiple different iterations of oxygen. So it can have 3 oxygens, it can have 2 oxygens, it can even have 1 oxygen or even 4 oxygens. Okay? Now. The most common version or combination of nitrogen with oxygen, right, gets the "ate" suffix. Okay, so here's the rules. I'll write them over here. Most common version of a particular oxyanion. I'll just do oxy for short. Gets the "ate" suffix. Okay. In this case, the NO3 is the most common combination. So we get, instead of having "ide" or anything like that, we remove the "ide" and we just get nitrate. Okay. Nitrate. NO3 is the most, this is the confusing component. NO3 is the most common combination of nitrogen and oxygen. Okay. That does not mean that having 3 oxygens is the most common combination with chlorine or with carbon or whatever. Okay. Each individual type of oxyanion has its own most common form. Okay. And that most common form has the "ate" suffix. Okay. So for example, on the other hand, something like SO4, 2-, right? That is the sulfate ion because it is the most common combination of sulfur and oxygen. Now, again, notice that the most common version of sulfur and oxygen has 4 oxygens. The most common version of nitrogen and oxygen has 3 oxygens. So again, just because NO3 is called nitrate doesn't mean that every other combination of sulfur, carbon, whatever, and oxygen needs to have 3 oxygens in order to be called nitrate. You start off by figuring out what is the most common version of that oxyanion, and you give that most common version the "ate" suffix. Okay, so that's our starting point. Okay, now, then what you do is you start adjusting how many oxygens are present in the oxyanion. Okay, so if NO3 is nitrate, you can have a version of nitrogen and oxygen where there's NO2, NO4, NO, right? And we start changing the suffix based off of where it is in relationship to the "ate" suffix. Okay, so if this has the "ate" suffix, okay, the one right beneath it, so if you have 1 less oxygen than the most common version, then we add an "ite" suffix. Okay, so NO2, right? NO3 is the most common version, so it gets the "ate" suffix. If I take away 1 oxygen from the nitrate, right, and then only have NO2, that turns it into nitrite. Okay. Down here with sulfate, I'm going to scroll down a little bit. Down here with sulfate, right, if I wanted to turn it into sulfite, I would take away one oxygen, and that would give me sulfite. Okay. So once you know what the 8 is for every specific type of oxyanion, then you start changing prefixes and suffixes, right, to tell you how many oxygens this has. Okay. In this first case, right, with the ite suffix, right, all that means is that it has one less oxygen than the most common version of that oxyanion. Okay. Now, in addition to this, there's also prefixes which do the exact same thing as ite and ate, right? They just either enhance or take away another oxygen. You can kind of see maybe where we're going with this in the case of nitrate and nitrite. Okay, this is nitrite, sorry. There we go, nitrite. Okay, if we want to have one more oxygen than the most common version, right? So if we want to have one more oxygen than nitrate in this case, then we keep the ate suffix, but we add a per prefix. Okay. So that means that NO4 then becomes per nitrate. Okay. The 8 tells me that it is close to the most common version, and the per tells me that it has one more oxygen than the most common version. Okay. So per nitrate, the per tells me that I have one more oxygen than the most common version. On the other side, instead of per, I can have hypo, and that is the prefix that says that it has even one less than nitrite. Okay. We still maintain the ite like before. Okay. But we add the hypo prefix. So in this case, instead of going nitrite, we take away another oxygen, and that gives us hyponitrite. Okay, hyponitrite. Again, the hypo tells me that there's one less oxygen in this particular oxyanion than there is in nitrite. So now what you can start doing is once you figure out what the most common version is, so nitrate or sulfate or what have you, right? Then you can tell how many oxygens are present in all of the other different permutations. So in the case of sulfate, we know that SO4 is sulfate. So that tells me that if I want to take away one more oxygen, right, and that would give me sulfite. That also tells me that if I were to call something hyposulfite, then that would be one less oxygen than sulfite, which would be two less oxygens than sulfate. So that would be SO2. Okay. And on the other hand, if I wrote down persulfate, okay, then that would mean that I would have one more oxygen than the normal sulfate. So this would be SO5. Okay. So the most common version of a particular oxyanion gets the ate suffix. All right. And then we can adjust the amount of oxygens present in that particular oxyanion by changing the suffix or the prefix. Okay. Normal, the most common version, has the ate suffix. One less than the most common version has the ite suffix. Two less than the most common version has the hypo prefix and the ite suffix. And then one more than the most common version retains the ate suffix, but adds the per prefix. Okay, I know that one's a lot and really, really annoying, but oxyanions are a pain in the butt for sure. Okay, sweet. Let's see. All right. Okay, now as before, I wanted to give you guys a series of anions that I wanted you guys to memorize. So I'm going to jot those down right here. Anions. Okay. So these would be fluoride. Oops. Should be minus. So fluoride, chloride, bromide, iodide. Notice that these are the halogens. Hydroxide, nitrate, perchlorate, then acetate. The acetate one's a really long one. If you just know it, that's the really, really long one, then then you're fine. If you just know, if you just know that the really, really long one is acetate, then you're good to go. So those are all -1 charged. As far as -2 charged, there's only a couple. So that's the oxide, the sulfide, the carbonate. So you know that's the most common version. And then the sulfate, which is the one we talked about before. Okay, so these are -2. And then finally, the only one I want you to know that's -3 is the phosphate ion. Okay, so we have our cations, we have our anions. I'll let you guys take a screenshot if you guys need that. But obviously you can return to this video at any time. Let's see, got another 10 minutes or so, probably. Hopefully we can get through in 10 minutes. Okay, now when we start naming ionic compounds, so I can expand this a little bit. When we start naming ionic compounds, all we do is we name the cation and then we follow that by the anion. Okay, so if I had something like sodium, this one, I would say sodium iodide. That's not too bad. If I had something like this, I would have iron 2 sulfate. That's not too bad. If I had something like this, this is +6, this is -6. I would have aluminum oxide. Okay, so all you got to do is name the cation, then name the anion, and then you're done. So that's not too bad. Let me rephrase that. That's kind of rough, but you can do it. I wholeheartedly believe in you. You guys have the skills. Alrighty. And plus we're going to practice it in class. So all we got to do is rep that and then we Gucci gang. Okay. Now acids. What is an acid? We're going to talk more about acids later on in the semester. But importantly, an acid is an anion along with enough hydrogens to neutralize the anion. Okay, so if we have chlorine, that's a -1 charge, so we have 1 hydrogen. If we have sulfate, which has a 2- charge, we have 2 hydrogens along with it. Okay, the rules aren't too bad as long as you can remember the anion at work. Okay, so for the first one, here's the rules. Rule 1. If there is an "ide" suffix, okay, if there's an "ide" suffix, switch the "ide" to "ic," Okay, so chloride goes to chloric, sulfide goes to sulfic, oxide goes to oxic, nitride goes to nitric. Okay, so if there's an "ide" suffix, the "ide" gets switched to "ic," right? And then add the hydro prefix. Okay, so for example, chlorine has a -1, so chloride. Okay, so the chloride goes to chloric, and we add a hydro in front. So that's where we get hydrochloric acid. Something like nitrogen, right? Nitrogen has a nitride suffix. So we switch the I to ic, so nitric, right? And then we add hydronitric acid. Fluoride has the switches from I to ic, so it becomes fluoric. And then we add a hydro in front, so hydrofluoric acid. Okay, so again, if you have an "ide" suffix, switch that "ide" to an "ic" suffix, and then add hydro to begin. So we go from something "ide" to hydro something "ic" acid, and then you're done. Okay, now as always, the oxyanions um, start to make things a little bit more complicated, sadly. But they're not too bad. They could be worse. Okay, so here's rule 2. Sorry, one second, guys. You probably hear my phone going crazy right now. No. Okay, so rule number 2. Okay, if you have an 8 suffix, okay, so again, that's the persulfate, sulfate, nitrate, pernitrate. If you have the 8 suffix, then what you're going to do is you're going to switch the 8 to an ic. Okay. You don't add the hydro. Okay. So nitrate becomes nitric acid. Okay. NO3 becomes nitric acid. Okay. Persulfate becomes persulfic acid. Pernitrate becomes pernitric acid. Okay. So if you have an 8 suffix as opposed to an "ide" suffix, if you have an 8 suffix, it switches to ic, right? And then you switch out and then you don't add a hydro or anything like that. So it's just nitric acid, persulfic acid, that sort of thing. If there is an "ite," so again, like nitrite, sulfite, this adds an "ous," and again, no hydro. All right. So sulfite becomes sulfus acid. Nitrite becomes nitrous acid. Okay. So if you have an 8 suffix, 8 switches to ic and there's no hydro. If you have an "ite" suffix, ite switches to "ous" and then there's no hydro. Okay. Again, the way you can figure out whether or not you do ic or ous or anything like that, or add a hydro or not, is if you have an "ide" as the suffix, then you're adding the hydro. Only if you have the "ide do you have the hydro added. Okay. The 8s and the ics and the ouses, that's specifically for oxyanions. Okay. Now, the last one that I wanted to talk about just briefly is going to be non-ionic binary molecules. Okay, so these are just molecular compounds. Okay. Now, in this, there's a couple of different rules. Rule number 1, I guess I don't need that, right? The element on the left and furthest down, oops, yikes, I don't know how to write today, and down goes first. Okay. So if you're further to the left and down on the periodic table, you're going to get named first. Okay. Rule number 2, the second element gets an "-ide" suffix. Okay. Then finally, you use Greek prefixes, so mono, di, tri, tetra, penta, that sort of thing, for each element, except the first, if only one. That's kind of a confusing one. That just means that if I'm blending two molecules together, let's call it X and Y. If I have 2 and 4 right here, then I use Greek prefixes to reference the 2 and the 4. But if I just have X and Y2, okay, I'll use the prefix for the second one, but because the first one doesn't have more than one, I don't need to do a prefix for that one. And that summarizes the binary molecules. They're actually really, really straightforward as long as you remember your Greek prefixes. So that would be mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octo for 8, nona for 9 to show you how frequently nona shows up. I had to go and squint there. And then finally deca for 10. Okay. Honestly, the ones that show up the most are 1 through like 5. Anyway, that is it. That is all I have. I'm going to save this picture and I'll send it to you guys if you so desire. But otherwise, that's all I have. I'll see you guys in class.